Stupid spot.
That is the stupidest
It's the
exit.
dumbest spot for an exit.
Where's an accident?
No, an exit.
Oh.
Then you're testing is
Oh,
in Howell Hall.
Okay.
You go in the front door, which makes enough sense, but then you come out like one of the side ones facing Oppenheim, so you have to walk all the way.
Oh, I don't go through pile of snow because
Yes. Yes.
So,
Excellent, excellent.
Also, do you like the solution to like instead of tying everything real early in the morning, just send out an email and say, be careful.
the website is not too bad.
Literally.
They're gone until like 3 a.m. Don't ask me how.
Oh god, that's
I wasn't
terrible.
All the noises invaded your dreams, and you had a dream of them taking care of the sidewalks and stuff.
That's that.
Okay, so I want to do a couple more examples. Well, one more example of showing you how FMU new is related to Ampere's law. Then I want to show you one other thing with it. Then I'm going to do a little bit more with it, but I think more through homework. And actually, I'll say one other thing. Did anyone print out that sheet I gave you with the? No one did. Okay, hang on. I'm going to pause this, Mike, so that there's not too much of a delay. I sent something. Okay, so what you're going to do is, let's just do a little bit here. So we have this FMU new. And how do we define FMU new formally? Partial?
Yes. Partial mu,
U.
and then
A. New.
mu minus
Minus.
partial mu a.
That's right. You flip the order. So like that. And we work this all out. We work out this as a matrix. As a matrix, what did it become? What do all the diagonal elements have to be? Zeros. Because it's anti-symmetric. And so remember, anti-symmetric means if you flip these, you get minus itself. So if you're on the diagonal, if you flip them, well, that's the same thing. It's not flipping them. So the only way you could actually have that be anything is for it to be zero. But they don't happen along this column here, or this row. And this is EX over C, Y over C, and EZ over C. Now, some books will just have EX, CY, EZ. What does that immediately tell you? So you're in natural units, okay? So then what has to be then this column down here? The minus of this. And zeros all the way here. And then this one here, okay, so this would be the, which element would this? This would be F2. It should actually be F1, 2. What is F1, 2? Yeah, notice you have a 1, which is an X, a 2, which is a Y. So these elements down here are always going to be the last one. So this is BZ. Yeah, so this would be B1, B3. So the X is there. The Z is there. So this has to be BY. Now, what's the other thing you have to remember? Yeah, the sign. This doesn't tell you the sign. So this is this one, but there's only one that comes in with the minus sign. And then this guy here then has to be, this is BX. And then this is just in the flip of these. That's what you have for this. And so one thing we did is that, okay, so this is a second rank Lorentz tensor. So the E and B fields are elements of a second rank Lorentz tensor. That's kind of neat. You think of the electric field as just being a vector. And it is when you're dealing with just, Newtonian physics. But when you go to relativity, it's actually a second rank Lorentz tensor, the elements of it. Okay, kind of new, cool. So what does that mean? That means you can actually write this as mu nu prime. And here's F, actually, I'm not going to put these here. F alpha beta. What would then go in here? As soon as you know this is a second rank Lorentz tensor, you can write something. Here are the A's. There's mu here. Mu alpha. So this is here, and then this is here. I have to do the same thing for the next one. So this one is going to be nu, and then this one's going to be then beta. So this guy's here, and this guy's here. Okay, we're going to have a lot of things like that. That makes sense? And we said we could actually write this in terms of a matrix, and so we ended up writing this, once we rewrote this as A mu alpha, A alpha beta, A nu beta. We need this to go the next one here so we could actually have matrix multiplication. So we took the transpose of this, which ends up looking like the same thing. We said this is the matrix multiplication. So we can write this as, and this gives you a big mess here, but then you can equate it to these elements over here. This would be 0, ex prime over c, ey prime over c, ez prime over c, and then so on and so forth, all the other ones. And then this would tell you the transformation equations. And what you should have got is I took that thing and I photocopied it from this book here. This is probably the book you're using in advanced CNM. This is a standard book. It's a very good book. He's an odd writer. He can do things really, really well or amazingly bad. This book is, I think for the most part, thumbs up. It's a good book. His quantum book is just weird. I mean, parts it gets better the further in you get. His book in particle physics is kind of all over the place, but it's one of the few books out there at the undergraduate level. But I don't use it anyways because I just do my own stuff.
It's Griffiths, right?
Yes. And if you do that, you end up with those equations I sent you. You end up with this. You end up with ex prime equals ex. Ey prime equaling gamma ey minus v bz, and then ez prime equaling gamma ez plus v
I don't think that's supposed to be a V.
It is b y. Okay, so that's what you should have got, and then the other ones are
But question, what is V?
the velocity of the of your. In other words, it's like the beta v over c.
Oh, okay, gotcha.
Put a c like top and bottom here, and that'd be beta.
Gotcha. Yep, that's what I got.
And then likewise for this guy, you get this. That's what you should have gotten. Okay, if you do it correctly. Now, this is really important here, and this is important here. It means that along the direction of motion, your electric fields don't change, those components. So if your frame are going along, if your S prime are going along the Y frame in the Y direction, then what component would be the same? The Y component. Okay. So often what books will do this, they'll call this the parallel component. They'll say E parallel prime equals E parallel here, meaning this is parallel to the direction of motion. And then these guys here get grouped into the perpendicular components. And you can actually make this a vector. How could you make this a vector in the perpendicular direction? For example, how do you think you would define E perpendicular as a vector? Vector. This would be E y j hat plus E z k hat. Okay, so I can multiply everything through here by the I hats here, so you can actually then write this in a more compact form. Okay. Now, what do you think going the other way would be? Suppose instead of these relate basically the S frames to the S prime frames. Suppose I want it to be flipped. What do you think those equations are going to be? Okay, so the v goes to minus v, and
Would you just switch the primes?
that's exactly what you do. So in a case like that, you get the following. Something I want to show you here, which is incredibly cool. Okay, let's take a special case, and I'm going to have you work out more details on this, and I think in the next homework, I'm tinkering with an assignment. I did hand out the third homework assignment, didn't I, do you guys? Okay. So let's take this case here. Let's say here's S prime. And I'm going to have a charge here. This is a charge at rest in S prime. Meaning that this charge is also moving with a velocity v along the x prime axis. Okay, what would then be ex prime, ey prime, ez prime, bx prime, by prime, ez prime? What would these things be? Okay, somebody know exactly what they would have to be, what they have to be.
They'll be 0.
Tell me what the 0 would be. Which ones?
The magnetic ones, because it's not moving.
Exactly. These all have to be 0 here, right? And these would not be 0. Because you have a point charge here, so you know in this frame here, the E prime vector S equal K Q over R prime squared. Right? So you'd have some point here like this. This would be R prime like this. And so the magnitude of this R prime would be then your X prime squared plus Y prime squared plus Z prime squared. Right? And then you can find out the components of it. Does that make sense? Now here's the amazing thing here. You have no magnetic field over here. But what about this in this frame here? Okay, what is this, this, and this? These are 0. This is 0. And this is 0. But you still have a by and a bz. Yeah, because you have these right here. And so notice, you can see immediately from this that the magnetic field is entirely coming from the Lorentz transformation. That's why we talk about electromagnetic interactions, because they're the same thing. It's really due to the transformation there. And this is what Einstein showed, is that Einstein showed this little connection here. Yeah, we're about to kill Ryan. His smartphone went off, so we're going to kill him now. Okay. I told him to wake up. Okay.
Dr. Alex, we talked about this. You need to stop the recording before
Oh, that's right. Before then Ryan disappears. I'm glad though he set the alarm for 15 minutes after class started. That's I'm glad about that. Okay. I'm giving you a hard time. It's good. Okay, so does this make sense? Okay. So this is really cool. Now I'll have you do some other things with this, and it's really kind of fun to do.
Can I ask a question that might be outside the scope of what we're talking about right now?
Sure.
So if you were at rest that if you were in S and you had the particle at rest in S prime, you would see the magnetic field when they would see no magnetic field, right?
Yes.
So could you interact with that magnetic field and take out energy? And how would that look in S prime?
Well, you can certainly, once you have a magnetic field, you know magnetic fields, you'd have to use a charge somehow to interact with it. And so because you have to put a force on it. And then you have to be careful because your forces are this QV cross B. So these are perpendicular. So it's often hard to extract work from magnetic fields because the force is often perpendicular to the direction of motion. But you would interact with that. I mean, you would have some sort of, it'd be a little tricky. But what happens is you have to look at how this thing develops with time. So if you're somehow taking energy away from the system, let's say you're starting to slow up this particle. Once you slow up this particle here, it's no longer in rest with S prime. So now you start seeing a magnetic field in that frame as well.
Gotcha.
These get ridiculously complicated. Does that make sense?
Yeah, cool. Thanks.
Yeah, it is actually really cool. Okay. Now, so we have that. Now I'll have you do some things where you can kind of see how more this works. Again, when I've taught this course before, I've never done this part. I always did it in, where I primarily do it is when I do the second semester of E&M. And often I can get there just toward the end of the first semester of E&M, but it's so quick, I don't think anyone really entirely gets it. Because that's a hardcore setting ways it comes at the very end, and this, it just feels like a tidal wave is hitting you, and that's, of course, feels like a tidal wave anyways, just under normal circumstances. Okay, so we had one other thing. So we also said we could write Maxwell's equations in terms of F mu nu. We had this guy here, partial of alpha F mu nu. And then what did we add to this? And this is your daily homework assigned for today?
The cyclic permutations.
The cyclic permutation of this. So the next one would be, okay, what's this next one then? If you cyclically permute this? Nu alpha mu. And this one is mu alpha. And what you're going to show for the daily homework is that this actually explicitly equals 0. Okay, and which ones did this give us? It gives us 2 of them. Which of the Maxwell's equations? No, not Gauss's. We did, but not with this one.
Was it the no name?
This gives a no-name equation.
And Faraday's?
In Faraday's law. So this is a vector equation. You get all the 3 components on it. You get the x, y, and z component number. Okay? And then this one here is a scalar, so you just get the 1. Okay? So we got 2 of those. Then how did we get the other ones? So this is one of them. What's the other one? Said partial nu F mu nu equals and this is mu naught J mu. Now some books will just have this. What does that mean?
Natural units?
Yeah, how do you get natural units out of that one?
You need an epsilon naught.
C is equal to what? 1 over the square root of mu naught epsilon naught. So this goes to 1. What would these both become?
1.
1 as well. Okay. So if C equals 1, mu naught equals 1, epsilon naught equals 1. So if you look at books in particle physics and general relativity, if you're wondering where all the mu naughts and epsilon naughts are and stuff like that, everything's one. That is very infuriating when you first learn it. And it just can get you sometimes frustrated and angry. Once you get used to it, it's hard to go back. You're going to realize the genius of this. But to realize that genius takes a lot of experience for that. When you're first learning it, it's really like somebody's cheating on you badly. Okay, so we didn't do Ampere's law for that one. So let's do Ampere's law. And so we said this one here gives us Gauss's law. Gauss's law when mu equals 0. And then we get Ampere's law, we get all the components when mu is not equal to 0.
And that's because we have to switch out of the mu. Or no, sorry.
It's going to come out when we trim this guy here. So let's actually do it. So do you want mu to be 1, 2, or 3? Pick one. 2. Okay, so let mu equal 2. So this is partial nu F2 nu equals J nu J2. That's actually hard to say. Okay, so what does this equal here? This is partial 0, F2 0, plus partial 1, F2 1, plus partial 2, F2 2, plus partial 3, F2 3. This is mu naught. What is J2?
JY.
Yeah, this is JY. All right, so now one of these is 0. Which one is 0? Yeah, remember all the diagonal elements are 0, so this goes out. This is 0. So now let's look up this. Okay, so what is this guy here? What is partial 0?
No, CT. Yeah.
Partial with respect to CT. I thought with the lower one it's always a negative.
No, because it's flipped.
Yeah, this one here is the oddball out. Okay, this one when it's down lower, the time component is positive.
Quick question, why did the Y component go out?
Because this guy here, F22 is 0. It's along the diagonal element.
Oh, right, yeah, okay, yep.
Okay. Now what is F2 0? Is what one? Yeah, it's going to be EY over C, but that's the positive one is when it's 0, 2. The flip one is the minus 1, so we get this guy. What is this guy? Hey, Mandela.
The X partial.
Okay, so partial with respect to X. What is F21? F12 is F12 is BZ. So F21 is
Minus B.
this guy is Z. And this guy is partial with respect to Z. This guy is
BX.
BX. Okay, so what is this guy here?
That's the cross product, the curl.
Okay, it's the curl of B. Which component? Is a Y component. So I'm going to take this to the other side. So this gives us y component equals mu naught jy plus 1 over c squared partial ey with respect to t. What do we do with that 1 over c squared? No.
That's a mu naught.
Yeah, c is 1 over the square root of mu naught epsilon naught. So 1 over c squared is mu naught epsilon naught. Okay? So I can rewrite this as in this mu naught jy plus mu naught epsilon naught partial ey with respect to t, or I can write it as y component.
Dr. Loud,
Yes.
I've always wondered, what is mu naught and epsilon naught? I feel like we've never really explained it.
They're, what they are the names are, this is your permeability of free space, and this is your permeativity of free space. And right at, when you use MKS units, there are more parameters that come in to get the units right. You could actually maybe have, there could be something more fundamental connected them with basically kind of the polarization of the vacuum. That's kind of more at a more theoretical level. But if you're in CGS units, they don't even exist. So you use these in MKS units. You don't even use these in CGS units. So if you're in CGS units, you won't see these guys here. And the way they're connected to the speed of light is this guy here. So the mu naught here comes in from Ampere's law, and the epsilon naught comes in from Gauss's law. I don't really have any physical interpretation per se, although some would argue that they do, depending if you start looking at the vacuum and start looking at how the vacuum can be polarized and stuff like this. Others? And some people really hate them, and that's why in natural units, in CGS units, you don't have them. And so you can look at a lot of older books that they won't even be here. So if you look at Gauss's law, we write is like this. What happens, you look at some older books, and they won't have this at all. They have this Q, and then there's a 4 pi here. Because they're in some version of CGS units. And this is perfectly fine, it's just they're not in, so there's also not at all. And Ampere's law then becomes, like this guy here. And you get this like 4 pi j in it, like this. I mean, I. And the other terms here. Then you get word factors of C. The Faraday's law becomes this. So you see word factors of 4 pi and C coming in. They're in some form of CGS units. There are a zillion different types of CGS units, and you can really spend a lot of time converting it in CGS units. So if you're in CGS units, they don't even come in. Others?
So if we let u equal 1 or 2, we get the cross of.
Yeah, so if this were 1, what would we end up with? The x component, and then 3? Z, exactly.
The exact same orange.
Yeah, it would look exactly like this, except with a x here, z here, z here. Okay? And if you take a course in particle physics, instead of having f mu nu, okay, so let's say you're looking at quarks. Instead of having f mu nu, you have g mu nu. And it looks just like the f mu nu term, but there's an extra piece on it. And then you can look at electroweak theory. There will be basically a w mu nu, which will look just like f mu nu, but with an extra piece on it. And so you can write Gauss's law. You can write Maxwell's equations for quarks. You can write Maxwell's equations for quantum electrodynamics. They just have extra pieces in them. It is. Okay? One more thing with this, and then I want to start T mu nu. Okay. We can also define a quantity K mu as, I'll tell you what K mu is. This K mu is going to be Q U nu like that. Okay. I haven't told you what this F mu is, this K mu is yet. We're defining it like this. Okay? We'll find out what it is. Well, I'll tell you what it is. This right here is going to be the Minkowski force. And it's going to be related to something else, and I'll tell you that in just a second. Okay? Let's let mu equal 1 and figure out what this is. Let mu equal 1 and solve for K1. All right, so I'll put K1 here. This is Q, this is U nu, this is F1 nu. So what does this equal? QU0, F10, plus QU1, F11, plus QU2, F12, plus QU3, F. Q. What is U0? Gamma. Remember this guy? We said is dx mu d tau. And we work this out. This is gamma C, gamma V. Okay. So this is Q gamma C, this guy. What is F10?
Negative EY over
So
C.
this is going to be minus EY over C. Okay, so I think I hate to do this, but.
Shouldn't it be X? EX?
Because it is X. Okay, this thing here, I think I remembered it wrong. I want it to be, don't write this down yet. So I want it to be the opposite sign. Okay, so this would be like F mu like that. Because it doesn't matter how you go here. So I want to sum on this guy here, then be left with that guy. Okay?
And by doing that, it changes the.
Yeah, so I should have this combination here. So let me see if I can fix this easily. If I go like this, one. Sorry about that. This guy's the same, woohoo. So we want yes. Okay, I'll let you tell me when you get that fixed in your notes, and I'll start. I apologize for that. Done?
Wait, where is the change? It still looks like you.
This, it doesn't matter how you write this guy here. The main thing is that I want to sum basically on the first index here.
Okay.
Okay.
So the way you had it written before doesn't imply you're summing on that index.
The way I had it, it's whatever the repeated indexes was when we were summing on it. And I had it summing on the other guy.
Okay.
So we had it before, I had it like this. Because I'm just used to writing after you knew. So you're summing on these instead of this guy here. Okay. Basically, because I don't want to get the negative sign. Okay. So we get this guy. What is this one? This is 0. What is this one? Q. U2 is? Oh, damn it! I was right to begin with. Sorry, guys. Tell me whether that was right. Okay, fix this again. Okay, tell me when you get that refixed. And then you're going to tell me where my mistake was. I apologize for that.
Was your mistake in how you were referencing the FMU matrix?
No. Okay, so we have this guy here. This guy is negative. And this is true. That statement is true. Tell me where my mistake was.
Oh, does gamma C have a minus sign on it?
Yeah, this guy is what? Minus gamma C, gamma B. I forgot that stupid minus sign. So this is, I'll put that little minus sign here. That. That's where my mistake was. Okay, tell me when you get that all fixed.
In my notes on that day, it's positive.
Everyone good to go? Okay. Now tell me about this guy. U2 is
So that's gamma V,
gamma V Y. F12. It has a 1 and the 2, so 1 is X, 2 is Y, so this is going to have to be the Z part. So it's going to be VZ. Plus or minus? It's plus. Plus Q, U3, gamma VZ. F13, minus BY. So these cancel here. And everything has a gamma in it. So I'm going to have now Q EX plus Q UYBZ minus VZBY. Hey, what is this? What are you crossing? V and B. So this is V cross B, which component? The X component. So what do you end up with? You end up with this K1 equaling gamma times QE plus QB cross B. And then you're looking at the X component there. Okay? So you call this the Minkowski force. I'm going to explain a little bit more about it. You basically get the regular force here, but then it gets multiplied by this weird thing of gamma. Okay? Does that make sense?
there any reason you can't pull the Q out as well?
You could, but normally, okay, what is QE normally? This is the force an electric field puts on a point charge, right? And what is this? QE cross B? No.
The force of a field on a particle moving through it.
Exactly, that's the force that a magnetic field puts on particle Q. Well, we have that we're a factor of gamma here, and we call it this K mu, and we call it the Lorentz force. I want to explain why it's called the Lorentz force, is because it's the way it's defined. Okay, so any questions about how this works? And I apologize for having that screw up there. Okay. So what is the formal definition of K mu? Okay, so K mu is called the Minkowski force. And it is the relativistic generalization of, okay. You know that you're going to write the force as mass times acceleration. But what's the adult way of writing the force in classical mechanics? And you've all had this.
dp dt?
Exactly. It's going to be dp dt. So what we're going to do, we're going to take this guy here and we're going to generalize it. And that's going to give us this guy here. So let's figure out how to do this. So we don't want to do, think about how we did this here. So how did we define? Let's ask, why did we define? U mu is this. It's going to be the same reasoning. Why did we define U mu like this? What was our?
Because dt wasn't a Lorentz scalar.
Exactly. This is a Lorentz scalar. This right here is a Lorentz 4 vector. And what did we want this to be? We wanted this to be a Lorentz 4 vector. Okay, so keeping that in mind, tell me how we're going to then generalize this. What's the generalization of this guy here? Yes. So we're going to call that K mu. It's going to be by definition the generalization of this. And think about this problem and then kind of generalize it to this. Exactly. So we're going to have dp mu. This right here is this is a Lorentz 4 vector.
Is P mu just mu?
What?
Is P mu just like the Rex mass times mu?
Yeah, so P mu is by definition M, which is the Lorentz scalar.
Yeah.
Times U mu. Yep. Okay, so that's this part. So what do we have to divide it by?
d tau.
Exactly. This right here, which is the Lorentz scalar. And that guarantees that this then is a Lorentz 4 vector. Let's look at the K1 component. See what we get. Hey, what's P1? Very appropriate that Mandela asked that.
MVX or MUX?
Yeah, this is
MU1.
D gamma M VX. Okay. What is this guy? Okay, this is dt over gamma here. This right here, this is just your relativistic momentum. So in some sense, I can just leave it here as a px. This is your px. So this is going to be what? Gamma dpx, and again, it's your relativistic momentum. It's this guy here over dt. Well, what is this going to be then?
Does the gamma come in squared?
No, because the gamma goes with this whole thing here. The whole thing there is px.
Right, but then there's another gamma on the bottom.
Yeah, this comes here, so that comes up in front because it's in the bottom here. So this whole thing here is px. So that's the px there. This has the gamma in it.
Gotcha.
Then this gamma gets flipped up here. This right here is nothing but our normal fx. So this k1 here is just really this gamma times dp1 dt, which is just this gamma times this fx. And that's what we found here. When we calculated this thing, we had that gamma times this guy here, and that was just the x component. That's kind of neat. Questions? Okay, so what we do tomorrow we actually we start looking at half of general relativity. Okay, the easiest half. But tomorrow, we actually find the mystery that is T mu nu. This is your energy momentum tensor. We're going to actually figure out how to calculate this thing. For certain cases, we're going to look at dust or kind of gas that's not just kind of gas. We're not going to look at basically what happens in kind of more abstract cases. This can get really, really complicated. The structure of it, though, is always the same, no matter what the elements are. So tomorrow what we're going to do is look at this, figure out how to construct it for some simple cases. And then I told you before, I'm working on a case where I'm going to have you work this out for the electromagnetic field. The problem is that the derivation from that is, okay, I'm stealing basically I looked at somebody who did it, and basically I'm stealing his proof and basically converting it into a homework problem. So all the different steps of the proof, I'm making like part A, then part B, then part C, so I can lead you through it. And the problem that I'm stealing it from, he tells the students, he says, if you get this problem right, I'll give you a bottle of wine. So, okay, are you familiar with the Scottish book problems? The math, okay, this is kind of interesting history. I can stop the lecture here. Actually, well, okay. So there's this, before World War II in Poland, there's some bar that mathematicians would hang out in. Imagine that, physicists and mathematicians at a bar. And they had a book on the table. And people would write problems in the book that they didn't know the solution to, or they thought were kind of challenging or just kind of fun. And it became known as the Scottish book problems. And what they did is, I don't know why since they're in Poland, but it became the Scottish book problems. And they'd give prizes for them. And so one of them said, well, this problem is worth a bottle of wine, or this bottle is worth some money, or who knows what. And it became actually quite famous. And so people would talk about these Scottish book problems. So I think the reason why this guy said this problem is worth a bottle of wine is he was thinking of the Scottish book problems. Eventually the Second World War happens, people take the book and hide it. But then after the war is over, they actually get the book back. And I think there's still a couple of Scottish book problems that have not been solved. Okay. I suspect the person who wrote them is dead, so you're not getting your bottle of wine or any money. But you will get the publicity of solving a Scottish book problem. Okay, have a fantastic day.
So if we get that problem right on our homework, do we get wine?
I won't give it to you. Maybe he will if you contact him. Okay. Okay, take care.